Hello, my dears. This is the material of week 2 for module 1. And this week we are going to study the Laplace transformation. The relation between input and output in any system is described by differential equation. The differential equation, which linear time invariant differential equation, as you see in here. So this equation is a description for certain system where RT is the reference or the input and CT is the output. So dealing with time domain is going to be very difficult. That's why we prefer to deal with Laplace. So any system, we are going to convert its transfer function to Laplace domain, perform the theory of control system, then the result to be converted back to time domain by finding the Laplace inverse. So in dealing with Laplace, we can describe the system as input, output, and the system, which is the transfer function. What is Laplace, or the definition of Laplace? Definition of Laplace is, any system can be converted, or any function can be converted to Laplace, or we can find its Laplace equivalent, as shown in this definition. So to do the Laplace for any function in time domain, it's to be expressed as a f capital of S, which to be calculated as the integration from 0 to infinity for that function as a function, the function in time domain multiplied into exponential of minus st, where S is a complex variable with real quantity and imaginary quantity. As I mentioned earlier, after calculating the requirement of system, we will convert the function to time domain. So we will find the Laplace inverse. So to find the Laplace inverse, we are going to convert it or calculate it by following this definition. It's 1 over 2 pi j, the integration of minus j omega to sigma plus j omega for the function in Laplace domain multiplied into exponential of st. Actually, the good point here, we are not going to calculate the mathematical functions in detail. Most of the time, we are going to depend on this table, which giving us ready functions. We are going to take it as it is. We don't need to do the calculation in detail. Like as you see here, delta t can be found in Laplace as 1 ut, which the step function can be calculated as a 1 over s. Its Laplace equivalent. Its Laplace equivalent is 1 over s. Tut, its Laplace equivalent is 1 over s squared, and so on. So whenever we have function in time domain, we are going to rearrange the function to put it in this format. Then we are going to find its equivalent from the table as shown here. Or sometimes we need to use certain theorem in Laplace to simplify the function, and it's going to make us easier for us to find its Laplace inverse. Partial fraction expansion is a method used to convert or to find the Laplace inverse. So this is what we are going to depend on here in control system. In control system, we are going to follow most of the time partial fraction expansion. So if a function f1 of s is given as n of s over d of s as seen here, or numerator over denominator, if we find that n is smaller than ds, then we can calculate the Laplace inverse directly. What will be the situation if n is greater than ds? The numerator is bigger than the denominator, or it's having higher order than the denominator. We have to divide it until we get the quantity as constant or certain variable plus numerator and denominator, where at that situation we are going to get n of s smaller than d of s. So this is to be seen in the next example, or in the example in the next slide. Like for example, in this example, if I want to calculate the Laplace inverse of this function, look, it's very clear here that the order of the numerator is higher than the order of the denominator. For that, we cannot apply the partial fraction expansion direct. We will divide the numerator over denominator. Keep in your mind, I didn't show the dividing here. Dividing steps, I didn't show here. So by dividing, we are going to end up with, this function is equal to s plus 1 plus this function. So when you look at s and 1, they can find, we can find them in the table direct, but this function we need to apply partial fraction expansion to it. Let me just erase this. So again, let me repeat this point. This one found in the table, this one found in the table, and this one we need to apply the partial fraction expansion to it. So now if I try to find the Laplace inverse from the table, you will find that s is d delta of t by dt, where 1 is delta t and this function is as it is. So we are going to apply Laplace inverse theorem to it. So as I explained earlier, now this function, we need to apply partial fraction expansion to it. So we are expecting to meet 3 cases out of this. We are expecting to see 3 cases out of this one. We are going to discuss them one after the other. Now case number 1. In case number 1, we call it root of denominator are real and distinct. If the root of the denominator are real and distinct, like what you see here, we have numerator, whatever the numerator is no problem, but the denominator is expressed as s plus p1 into s plus p2 into s plus until pm until pn. If the case is like this, then we call the function as real and distinct. So to find its Laplace inverse, we need to apply partial fraction expansion, where we need to find the equivalent to this function, which can be found in the earlier given table. So we can put the function, this function, as k1 over s plus p1 plus k2 over s plus p2 and so on till the end. So now to calculate any of these constants, k1, k2, k3 until kn, to calculate it, we are going to apply this idea. So km is equal to s plus pm multiplied into the function, the whole function, and we solve it at s equal to minus pm. Let us see this in the next example. So like for example, in this function, f of s is equal to 5s plus 3 over s plus 1 into s plus 2 into s plus 3. So f of s here can be written as k1 over s plus 1 plus k2 over s plus 2 plus k3 over s plus 3. So now if I find the constants k1, k2 and k3, that means I am finding equivalent to this function, which we can solve it from the table direct. So how to calculate k1, k2 and k3? To calculate k1, we are going to get the denominator of k1 from here, this value s plus 1. So s plus 1, we take it here, and we multiply it in all f of s. We will multiply it in all this function. If you notice, we multiply it in all this function. So of course, s plus 1 will cancel s plus 1. The remaining will be 5s plus 3 over s plus 2 into s plus 3. So we solve this one. We solve it at s equal to minus 1. Notice here, in the denominator of k1 is s plus 1, which help us to evaluate the k1 value by calculating it at s equal to minus 1. So we replace each s in the remaining function by minus 1, and we will calculate it to find k1 equal to minus 1. That's how we can calculate K1. Similarly, we can calculate K2, and it's equal to 7. And here we can calculate K3, which to be found equal to minus 6. So now we substitute the value of K1, K2, and K3 in the function given earlier. So f of s will be equal to minus 1 over s plus 1 plus 7 over s plus 2 plus 6 minus 6 over s plus 3. Now, if you compare these quantities with what is given in the table earlier, you will find that this function from the table is equal to minus 1, the constant is minus 1 here, exponential of minus t, plus 7, the constant is 7, exponential of minus 2, exponential minus 2t, minus 6 will be taken as it is, it's a constant, exponential of minus 3t, and that's it. This is all ut. So that's how we find the Laplace inverse of that kind of function, which we call it real and distinct. Here we can solve differential equation by the help of Laplace transformation. So we are given a function here. He's saying given the following differential equation, solve yt if all initial conditions are 0. So we need to calculate y of t. Out of this function, we need to calculate the value of y of t. So the function, if you notice, is in time domain. Simply, we can convert it to Laplace. When I convert it to Laplace, I'll be able to calculate y of s, and from y of s, we can calculate the Laplace inverse to get yt. So converting the function to Laplace, this quantity d square y by dt square is equal to s square y of s, and then 12 dy by dt is replaced or converted as 12s y of s. I mean, from the theory of Laplace, if you notice earlier, the derivative is equivalent to s in Laplace domain. The derivative in time domain is equivalent to s in Laplace domain. And finally, 32y is equal to 32y as it is, and 32y u of t, 32 u of t, you remember u of t in the table of Laplace, I mean, when you put it in S domain, it's going to be 1 over S. That means 32 u of t will be 32 over S. Now, we can use the algebra to calculate y of S. So y of S will be found to be this value. Now, if you notice, it's real and distinct. The function is real and distinct. So we can find its equivalent. So its equivalent is k1 over s plus k2 over s plus 4 plus k3 over s plus 8. Now we can calculate k1, k2, and k3 similar to what we have done earlier. You will see them in the next slide. So here is k1 equal to 1, k1 equal to 1, k2 equal to minus 2, and k3 equal to 1. We substitute them in the previous equation. We will get ys equal to 1 over s minus 2 over s plus 4 plus 1 over s plus 8. Now, if we compare the quantities with the table given earlier, 1 over s is a unit step, 1 unit step, so it's equal to u of t, and 2 over s plus 4, 2 is the constant, so 2 is remaining as it is, and it's exponential of minus 40 ut, and plus this value, the constant is 1, exponential of minus 8t. So we can rearrange the function to look like this. So this is the solution of the differential equation given earlier. So y of t is equal to 1 minus 2 exponential of minus 40 plus exponential of minus 8t.